Hi, I am Rajani.
And I'm Pedro.
This is Project 2133, the Convergence of HPC and Big Data.
What is HPC? HPC is born out of a need to tackle problems that are too difficult for a single computer to solve. These problems are called expensive computationally. In a basic HPC architecture, you use your personal computer to connect to a login node of an HPC system, usually with some sort of authentication like SSH keys. From there, you can submit tasks in batches into the queue using Slurm, and the compute nodes will perform this task and later interface with storage to give you back your output. The key word here is parallelize.
What is Big Data? Generally, there is no precise definition for this. Simply, we can say data whatever gets you into trouble, processing in serial. The challenges of the Big Data. The main challenges of the Big Data can be represented through 5 V's. The first V represents the volume, which is the amount of data that is produced, and the second V represents the velocity, and it is the speed at which the data is generated, collected and analyzed. The third V is the variety, and it refers to a class of data which can be structured, semi-structured or unstructured. And the fourth V is the value, which refers to the usefulness of the gathered data. And finally, the fifth V represents the veracity, and it refers to the quality of data.
High-performance data analytics is the term used to define the convergence of HPC and big data. HPDA offers the user the leverage of the efficiency of HPC systems in processor-bound tasks and big data in memory-bound ones, allowing new implementations of applications that use distributed storage as a resilient feature. By exploiting the compute power of HPCs, also allowing for real-time processing. However, there are some challenges like performance bottlenecks, the architecture and ecosystems, the high cost of moving data, and identifying the correct tasks that are suitable for automatic parallelization.
The Apache Hadoop software is a framework that allows for the distributed processing of large datasets across clusters. It consists of 3 main components. The HDFS stores the dataset in different blocks. The MapReduce is for processing the data in parallel, and the RAM is job scheduling and resource management layer. Apart from that, Hadoop is a highly scalable model and support fault tolerance by making 3 copies of each file blocks stored it into different nodes.
Spark is a cluster computing framework created by Matisse Haria based on Hadoop, with resilient distributed datasets as a data structure and other novel secondary ones like data frames and parquets. It's a lazy evaluation framework that supports real-time processing and has significant speed improvements in tasks that reuse a working set of data across multiple parallel operations, while retaining scalability, resilience, and support in many languages and libraries.
The project is based on the exploring convergence of big data and HPC in such a way that both will take the advantages of each other, and here we will explore this convergence on some scientific dataset.
Our strategy's first step is to read, pre-process, and transform our serial scientific applications data, for example, if we have a .csv file, into a Spark data abstraction, like a data frame or ultimately simple RDDs.
Once the dataset read into Spark RDD, the second step includes applying various trivial and serialized functions on the datasets. For example, based on our needs, we can perform different queries, group by, sort, and filtering functions on the dataset.
Step 3. Attack your for loops. Fors, whiles, recursiveness, and loops in general are all bottlenecks in our code. How can we make Spark understand them to be more efficient? Use and exploit user-defined functions where you can perform row-wise operations using lambda functions. At all costs, avoid collect and serializing RDD data.
Our final step is to test small and then build big. To test, use Jupyter notebooks with small sample of data. This allows us to benchmark early your code versus your legacy serial versions. If you run into trouble, try to create minimum reproducible examples. Once you are ready, create your Slurm file and submit it to our HPC system, and have a coffee until the job finishes. In this project, I have used the IMAGE dataset as a case study. IMAGE is a precipitation product of GPM mission from NASA, which provides precipitation dataset of the entire globe. The dataset contains precipitation in daily resolution, which comes in netseria format. Each file has 30 MB large, so the entire datasets from 2000 to 2020, which covers 20 years of daily precipitation, is around 230 GB. We have used the Spark R and Sparkly R functions to process the datasets.
Our second use case dealt with the post-processing of computational fluid dynamics simulations, results obtained from OpenFOAM with an initial Python script that was ported into Spark. It required an initial read step in which high parallelization was obtained and 3200% improvements in performance, a nearest neighbor search which found a performance degradation using a Spark library, and the computing of the gamma method which was scalable and parallelizable, but only if taken on a frame-by-frame basis. We would really like to thank Praise and Vienna Scientific Cluster for having hosted us during this summer of HPC. Thank you Leon, Giovanna, Dieter, Liana and Claudia. It's been fantastic.